Assalamualaikum warahmatullahi wabarakatuh. So this is a lab session 7. The title is System Response Frequency Response. So in this lab session we have to do a dot plot from the transfer function k over s plus 5, s plus 2, s plus 50. So we have to assume k and do a calculation and generate dot plot of the system using MATLAB. So this is the calculation that we have been made. The value that we get from the dot plot from the calculation is 15.56. So we assume k equal to 3000. So we do a magnitude plot, and this is the plot that we get, and the PM that we get is 117 degree. So this is a phase plot that we get. So this phase plot that we get, which is negative 24 dB. So we doing a calculation and get the range of the k, or range of the stable value for the k, which is 7924.47. So range of the k is 500 to 7924.47. So after that we do the MATLAB session to get a dot plot, and then we put the numerator and denominator as usual, and then after running this code we have to put the k that we assume, which is 3000. So after that we get the board diagram. So for the magnitude plot we get the gain 16.5, and the phase plot we get the 45.2 degree. So this is a closed loop that we've been searched. So the both part have stated yes, which is stable. So we have compared the approximate value from the calculation and the value from the MATLAB, and we conclude that there is a parallax error during making the dot plot, because there is a big gap from the value between the MATLAB and the calculation. Thank you.
So, for the discussion, when activated with a proper signal input, the system response is the output of the electronic system. Gain, frequency response, phase response, and distortion are all examples of response. For step response, it refers to the time domain system's output version to a quick low to high input signal. In the case of impulse response, the time domain system output response is caused by short duration and high amplitude impulse input signals. This is because both the step and impulse signals in the frequency domain have a wide spectral content dispersed across a wide bandwidth. It is frequently used to analyze system response stability, such as overshoot, understood, ringing, and so on, with a single test. This replicates real-world conditions where there are frequent variation in current load. For gain margin, the higher the gain margin, the more stable the system. The gain margin is the amount of gain that may be raised or lowered without causing the system to become unstable. It is commonly stated in decimals. The gain margin can usually be read directly from the dot plot, as illustrated in the findings, or in this case, our results. The vertical distance between the magnitude curve and the x-axis is calculated at the frequency when the dot phase plot equal to 180 degrees. This is referred to the phase crossover frequency. The formula for gain margin can be expressed as Gm equal 0 minus of G dB, where G is the gain. And for the phase, margin, the bigger the phase margin, the better the system stability. The phase margin is the amount of phase that may be raised or reduced without causing the system to become unstable. It is commonly stated as a degree phase. As in the result, we can generally interpret the phase margin directly from the bird plot. The vertical distance between the phase curve on the bird phase plot and the x-axis at the frequency where the bird magnitude plot is equal to 0 decibel is calculated. This is referred to as the gain crossover frequency. The formula for phase margin can be expressed as Pm equal phase minus with a negative of 180 degree. The phase is the phase lag where a number less than 0. This is the phase as read from the vertical axis of the phase plot at the gain of crossover frequency. So, for the conclusion, the frequency response explains a system's steady-state reaction to a sinusoidal input of varied frequency and allow control engineers to assess and grab frequency domain control systems. And a bar plot, as for definition, is a graph that is often used in the control system engineering to assess a control system stability. The bar plot has the benefit of being based on asymptotic approximation, which gives a straightforward approach for plotting the logarithmic magnitude curve because we are using a logarithmic scale. Multiplication of various magnitudes in a transfer function may be viewed as addition, while division can be treated as subtraction. Only with the assistance of this plot, we can instantly comment on the system stability without performing any computation. In terms of gain margin and phase margin, both graphs show relative stability. It also spans the frequency spectrum from low to high. That's it from me. Thank you very much.